So, in the fall of 2013, millions of people woke up, they updated their iPhones to iOS 7, and they just sort of stared at their screens trying to figure out what was wrong.
Or, what was suddenly so uniquely right about it.
Yeah, exactly. Because the apps looked completely different. They felt, I don't know, softer, more organic, like somehow more premium.
Right, and most people couldn't really articulate why that was. They just knew the grid of icons felt less like a rigid computer screen and more like a tray of perfectly polished river pebbles.
Which is such a great way to describe it. Because what they didn't realize was that Apple had just fundamentally altered the mathematics of a simple square.
They absolutely had.
They banished the standard rounded corner entirely and introduced the digital world to the squircle. And today, for your custom deep dive, we are going to teach you exactly how to read that hidden math.
We really are. We're dissecting the actual architecture of modern interfaces today. And our foundation for this exploration is, well, it's the Basic Elements chapter from a truly foundational text called Designing in Figma, a masterclass in modern interface design.
Such a good book.
It really is. We are basically stripping away the glossy surface of the interface to look at the raw mechanics underneath it all.
And, if you are already working in the field, maybe you know how to draw a rectangle or place some text, but knowing how to click a tool is vastly different from understanding why the software's rendering engine actually calculates that object the way it does.
Oh, completely different.
Right, because the tools we use today, they might share names with the tools from 20 years ago. I mean, you still have a pen tool and an ellipse tool, but their underlying physics have been completely re-engineered.
Yeah, they're totally different beasts now.
Exactly. So our mission today is to give you that X-ray vision. So you aren't just like pushing pixels around on a screen, but actually commanding the digital canvas. It's kind of like opening a new design app is like sitting in the cockpit of an airplane.
Oh, that's a perfect analogy.
Hundreds of buttons, super intimidating at first, but today we're going to learn what the most crucial levers do, one by one.
And to command that canvas, you first have to understand the laws of physics that govern it, which means, we have to talk about how things move and scale.
Let's start right there. The Move tool, shortcut key V. I have to be honest, when I first read this chapter, spending time on the Move tool felt a little bit elementary to me.
Sure, I mean, it's the basics.
Yeah, you click a box, you drag the box. It's the default state of a mouse. But the text treats it like this complex manipulation engine. Why is just grabbing an object considered a master skill?
Well, think about the actual structure of a modern web application. You don't just have a single box floating on a screen.
Right.
You have a text layer, and that text is grouped inside a button shape. And then that button shape is nested inside a navigation container.
That's like Russian nesting dolls.
Exactly. And that container is locked inside a global header component. So if you just take your standard cursor and click on the word submit, the software's default behavior is to select the largest parent container.
Which is the entire header.
Right.
Which means to change the word submit, I end up having to double-click to open the header, and then double-click to open the navigation container, double-click the button.
It breaks your flow state completely.
It totally does. It's so frustrating.
And that cognitive friction is exactly what the Move tool is designed to bypass, provided, the modifier keys.
Okay, lay them on me.
So if you hold the Command key on a Mac or Control on Windows while you click, you execute what's called a deep select.
A deep select.
Yeah. You are basically telling the rendering engine to ignore the entire hierarchy of groups and containers and immediately latch onto the deepest nested object directly underneath your cursor.
Wow. So it's an instant bypass. You just pierce straight down to the core layer without all the double-clicking.
Exactly. Furthermore, the Move tool functions as your primary spatial measuring device.
Oh, right, the proximity lines.
Yes. Because interface design is entirely about relationships, right? Like how far apart elements are. If you select an object, hold the Option or Alt key, and hover over anything else on the canvas, the engine instantly calculates the pixel distance and draws these red proximity lines.
You aren't just guessing if a gap is 20 pixels or 24 pixels anymore.
Nope, it's exact math.
I use that constantly.
Yeah.
But here's a mechanical question for you.
Yeah.
Let's say I measure that gap and it's 24 pixels,
Huh.
but my design system dictates it needs to be exactly 20.
Okay, sure.
I usually grab the edge of the bounding box and try to drag it to shrink the object, but my mouse is too sensitive and I always overshoot it. Is there a mathematical way to handle that without dragging?
Oh, absolutely. The keyboard is your precision instrument here. With the Move tool active, holding Command and tapping your arrow keys resizes the object's bounding box exactly 1 pixel at a time.
Just 1 pixel.
Just 1. And if you hold Shift simultaneously, you invoke the big nudge, which defaults to jumping 10 pixels at a time. You are totally overriding the analog imprecision of a mouse with pure digital increments.
That is huge. But that distinction between the bounding box and the object itself, it brings up a huge point of confusion for a lot of people.
It really does.
We have the Move tool, shortcut V, which lets you resize things. But there is a completely separate tool called the Scale tool, shortcut K.
Right.
If I can just drag the corners of a box with the Move tool and hold Shift to keep it from stretching out of proportion, why did they dedicate an entire separate tool just to scaling?
You're hitting on a core paradigm shift in vector graphics here. It really comes down to understanding what a bounding box actually is.
Okay, what is it?
A bounding box is just a mathematical container. When you use the Move tool to resize an object, you are only changing the dimensions of that invisible container.
Not the object itself.
Right. The properties attached to the object, like the thickness of its outline, which we call a stroke, or the blur radius of its drop shadow, they do not care about the container. They remain completely static.
Let me try to visualize this. It's like having a physical photograph inside a wooden frame, and the wood is exactly 1 inch thick.
Okay, I like this.
If I use the Move tool to drag the corner and make the frame twice as wide, the opening gets bigger, but the wooden border stays exactly 1 inch thick.
A perfect analogy. The container stretches, but the styling doesn't.
Makes total sense.
But what if you don't want to stretch the frame? What if you need to take an intricate, incredibly detailed icon you designed for a mobile phone and blow it up to print on a massive presentation billboard?
Oh, I see. If you use the Move tool, the icon gets huge, but all the lines stay razor thin.
Exactly. It looks skeletal and completely broken.
Because the strokes didn't grow with the container.
Great. And this is the sole purpose of the Scale tool. Activating K tells the engine to proportionally multiply every single mathematical value associated with that object.
Everything scales.
Everything. The bounding box doubles, the stroke thickness doubles, the corner radius is double, the shadow depth doubles. The Scale tool basically acts like a photocopier magnifying the entire composition.
So knowing when you are resizing a container versus scaling a composition is critical.
It's the difference between a clean file and a mess.
Totally.
Huh.
So we know how to manipulate the physics of the objects. Now we have to actually forge the objects themselves.
Let's do it.
Let's dig into the shape tools, and I want to go straight to the Ellipse tool, shortcut O, because the way Figma handles a simple circle is honestly wild.
It entirely removes the need for complex, destructive pathfinding.
How so?
Well, in traditional software, if you wanted to design a circular progress meter, like a ring that is, say, 75% full, you had to draw a big circle, then draw a smaller circle inside it, tell the software to punch the small one out of the big one to make a donut,
Sounds exhausting already.
and then draw a massive triangle to slice out a 25% chunk.
And if your client looked at it and said, actually, can we make the progress ring a little bit thinner? You were dead in the water.
You had to delete the shape and rebuild it from scratch because you completely destroyed the original geometry.
Wow.
But Figma recognized that pain point, and they totally re-engineered the ellipse. When you draw a circle, you'll notice a tiny, almost invisible handle hovering on its right edge.
Oh, the arc tool.
Yes, the arc tool. Pulling it down instantly slices the circle open like a pie chart. It manipulates a property called the sweep, which is measured in angular degrees.
It's basically like opening Pac-Man's mouth.
Yes, and the moment you change that sweep, the engine surfaces 2 more hidden parameters.
Oh, were they?
Well, the start handle lets you rotate where that slice begins on the axis. And most powerfully, the ratio handle appears in the dead center.
A ratio handle.
Dragging that ratio handle outward hollows out the core of the shape, instantly converting your pie chart into a ring.
That is so fast.
And all of this remains completely fluid and non-destructive. You can change the thickness of that ring 6 months later just by sliding a percentage value.
It's treating geometry as a live variable instead of a baked result. That's brilliant. But speaking of shapes, I have to bring up the arrow tool. Shift L.
Oh boy, the arrow tool.
Yeah, because the author of Designing in Figma explicitly states this tool, quote, shouldn't exist.
It really shouldn't.
Why would developers code an entire tool and give it a keyboard shortcut if it's functionally useless?
It's a fascinating compromise between feature discoverability and advanced functionality. The arrow tool is, frankly, a redundant interface crutch for beginners. Yeah. When you use it, the software is just drawing a standard line and automatically appending a triangular graphic to the endpoint. The fatal flaw is that the size of that triangle is mathematically bound to the stroke weight of the line.
Meaning, if I want a hairline, thin line, but a massive aggressive arrowhead pointing at a specific button, I just can't do it.
No, you can't.
Shrinking the line shrinks the arrow.
Right. It restricts your design vocabulary.
Yeah.
The professional method is to completely ignore the arrow tool.
So what do we use instead?
Use the standard line tool or the pen tool. Once your line is drawn, navigate to the advanced stroke properties in the inspector panel. Here, you have total independent control over the caps of the line.
The caps.
Yeah, you can append triangles, circles, diamonds, or reverse arrows to either end of the path and dictate their scale completely independent of the line's thickness.
Oh, that is so much better.
The arrow tool exists purely so someone opening a design app for the first time doesn't panic when they can't figure out how to point at something.
That makes a lot of sense. Keep the advanced properties hidden until the designer actually understands the stroke mechanics.
Exactly.
Now, let's talk about the Apple squircle we brought up at the very beginning, because this is where digital design tries to mimic the physical world.
The term squircle refers to corner smoothing, and it revolves around the mathematical concept of a continuous curve, specifically what's called a clothoid curve.
A clothoid curve. Okay.
To understand why it's revolutionary, we have to look at the alternative, which is the standard CSS border radius.
Which is how almost the entire internet is built. If I code a web button with rounded corners, I'm using border radius.
And border radius relies on incredibly basic geometry. You have a perfectly straight line, and at a specific mathematical point, it instantly transitions into a perfect quarter circle arc, and then instantly snaps back into a straight line for the next edge.
It's very abrupt.
It's a jarring, abrupt transition. The human eye can subliminally detect the exact pixel where the straight line dies and the curve begins.
But physical objects don't wear down like that.
They don't. Think back to the river pedal analogy. Water doesn't erode stone into perfect quarter circles.
It's organic.
The erosion is gradual, a straight edge slowly begins to bend, the curvature accelerates until it hits the apex of the corner, and then gracefully decelerates back into the next straight edge.
There's no single point of transition.
Exactly. Apple brought this industrial design concept into their digital interface with iOS 7.
And Figma actually built this algorithm into their software. I found this in the individual corners section of the properties panel. There is this hidden corner smoothing slider.
Yes, and if you look closely, the slider has a very specific notch at exactly 60%.
60%.
That 60% mark is the exact mathematical curvature used by Apple's iOS platform.
So, hearing all this, my immediate instinct is to just use the 60% squircle for absolutely everything I design. I mean, if it looks more natural, more premium, and easier on the human eye, why wouldn't I use it for every web button, every drop-down menu, every card?
Because the medium dictates the math. And honestly, doing that would make your engineering team absolutely despise you.
Wait, really? Why?
Web browsers are rendering engines that read CSS. As we established, CSS understands border radius. It is incredibly computationally heavy and complex to force a web browser to render a non-standard clothoid curve using custom math.
So the browser literally can't easily draw the squircle.
Correct. If you design a gorgeous web interface using 60% corner smoothing on everything, the developer's just going to look at it, sigh, and write a standard border radius line of code.
So the live product won't even match your design.
Right. The final live product won't match, and you will have wasted your time. You must reserve corner smoothing strictly for iOS app design, or for creating static illustrations and icons that will be exported as flat image files like PNGs or SVGs, where the math is baked into the graphic itself.
That is a phenomenal distinction. Know your medium.
Exactly.
But what if we want to abandon strict math entirely? The text touches on breaking the grid using plugins, specifically one called Blobs by Dylan Feltus.
Plugins are basically external scripts that interface with Figma's API to automate complex tasks. And when geometric perfection feels too clinical or rigid, designers often need organic, fluid shapes, usually for background aesthetics or masking.
Right, like those soft shapes behind illustrations.
Yeah, but trying to manually draw a perfectly random, smooth blob with the pen tool is surprisingly difficult because humans naturally lean towards symmetry.
We can't help it.
We really can't. So the Blobs plugin uses algorithmic generation. You set a complexity slider and a contrast slider, and the software generates mathematically smooth but entirely random, non-symmetrical vector shapes.
It injects controlled chaos right into the canvas.
I love that. And, these organic shapes transition us perfectly into how we handle real-world imagery.
Oh, yes. Place image.
Yeah, because in older software, if I imported a photograph, it just sat on the canvas as an image object. But modern UI tools don't treat images as objects, do they? They treat them as elastic material. This is a monumental shift in rendering architecture. To really grasp it, we must cleanly divide visual assets into two categories: vectors and rasters.
Let's start with vectors.
Vectors, like SVG files, which stands for Scalable Vector Graphics, are fundamentally just text files containing mathematical coordinates.
And the text highlights an amazing trick here for borrowing SVGs from the web.
Yes, it entirely eliminates file management. Because an SVG is just code, you don't actually need to download a file to your hard drive.
So what do you do?
If you find an icon on a website, you can right-click, select Inspect Element in your browser, find the HTML tag that says SVG, copy the raw block of code to your clipboard, and simply paste it onto the Figma canvas.
That is mind-blowing.
The rendering engine reads the code and instantly draws the fully editable vector paths right in front of you.
It's basically teleporting the math from the website directly into your software. But that's vectors. Raster images, like a JPEG photograph of a landscape or a PNG of a person's face, they're fundamentally different.
Very different. They are grids of static, colored pixels.
Which is why Figma doesn't treat them as independent objects.
Right. When you place a photograph onto the canvas using Shift-Command-K, what the software is actually doing behind the scenes is drawing a standard vector rectangle and then applying your photograph as an image fill to that rectangle.
It's painting the photograph onto the geometry.
The brilliance of this approach is elasticity. Because the image is just a fill property, it isn't bound to the rectangle. You can drag a photograph from your desktop and drop it directly onto any custom shape.
Oh, wow.
Did you generate an organic shape with the Blobs plugin? Drop a headshot onto it, and the software instantly masks the photograph perfectly to the irregular curves of the blob.
The shape literally becomes a window looking into the photograph.
Yeah.
I've used this constantly for user profile avatars. But there is a massive workflow friction point here.
The resolution problem.
Yes.
Yeah.
When you drag a high-resolution photo from a modern camera or stock site into your file, it often drops in at its raw native resolution. Maybe it's like 4,000 pixels wide. It just blows up your entire screen.
It's huge.
And if I needed to fit into a tiny 150 pixel avatar circle, dragging the corner to scale it down takes forever.
This brings up one of the most elegant quality of life features in modern design tools. The input fields in the Properties panel, where you type the width and height of an object, are not static text fields.
They aren't?
No, they are fully functional mathematical parsers.
This blew my mind the first time I realized it.
It's so good. If an image imports at 4,000 pixels wide, and you know you need it to be exactly 150, you don't need to do the math in your head. You don't need to manually resize it.
Just type it in.
You just click into the width input box, which says 4,000, delete it, type 150, and hit enter. Or if you just want it to be a quarter of its current size, you leave the 4,000 there and type /4.
You can type +24 or *2 to double it. The interface itself handles the arithmetic. It's a tiny detail, but it profoundly respects the designer's cognitive load.
Cognitive load is the exact right term, and preserving the designer's mental energy was actually the primary catalyst for the single greatest innovation in this software: vector networks.
Okay, yes. We are moving from basic shapes to drawing from scratch. The pen tool. I want to spend significant time here because the book notes that when the founders of Figma built their pen tool, they didn't have a background in legacy design software like Adobe Illustrator.
Which was an advantage.
Right. They looked at how traditional paths were constructed and realized the underlying logic was fundamentally broken.
To understand the fix, we really have to understand the broken legacy logic first. Traditional vector graphics operate on what is effectively a single linked list. A path is a single continuous chain. Point A connects to point B, which connects to point C, which connects to point D.
Like a single train track running down a coastline.
Precisely. Now imagine you are drawing a complex isometric illustration of a 3D cube. You have a point at the front corner of the cube. In reality, 3 different lines need to converge at that single corner point. The line coming from the top, the line coming from the left, and the line coming from the right.
Okay, I'm visualizing it.
In traditional software, because a path can only be a single continuous chain, a point cannot have 3 lines branching off it.
Wait, really? So what did designers have to do?
They had to fake it. They had to draw 3 completely separate, independent paths and painstakingly dragged the endpoints of all 3 paths so they stacked perfectly on top of each other, creating the illusion of a single corner.
That sounds awful. Your layers panel would be flooded with dozens of disconnected lines.
It was. And if the client asked you to move that corner a few pixels to the left?
Oh no. You'd have to carefully select the endpoints of all 3 separate lines and try to drag them together without breaking the illusion. It was an administrative nightmare. So how does a vector network solve this?
By abandoning the linked list entirely and utilizing graph theory. A vector network is like a massive subway interchange. Within a single vector network object, a single point can have any number of paths branching off it simultaneously.
Any number.
Yes, point A can connect to B, C, D, and E all at the same exact time. The math understands it is a single, coherent web of geometry.
So you can just grab that one corner point of the 3D cube, drag it to the left, and all 3 connecting lines stretch dynamically with it.
Exactly.
It's incredibly elegant. But to build that subway interchange, we have to navigate the terror of Bezier curves.
They are intimidating, for sure, but they are governed by strict physical rules. The cubic Bezier curve was mathematically formalized in the 1960s by Pierre Bezier, an engineer at the Renault car company.
The car company.
Yeah. He needed a mathematical way to describe the sweeping aerodynamic curves of a car's chassis so that automated milling machines could precisely cut the metal. He needed a way to translate a physical curve into pure data.
And we are still using his car math today. So let's visualize this for the listener. I activate the pen tool, shortcut P. I click once on the canvas. I've laid down my first point. I move my mouse and click again. Straight line connects them. But how do I make it curve?
The curve is generated by tension, and that tension is controlled by handles. When you click to place your second point, instead of releasing the mouse, you click and drag outward. This action pulls out a handle.
And what does the handle do?
At the end of the handle is a control point. The handle doesn't actually draw anything on the canvas. It is an invisible magnetic vector.
A magnetic vector, I like that.
Think of the line between your 2 points as a piece of flexible steel wire. The handle acts as an electromagnet. As the wire leaves the first point, heading toward the second, it is magnetically pulled toward the handle, extending out into the air.
So it bends the wire.
Yes. The length of the handle dictates the velocity or the strength of that magnetic pull. A short handle gently bends the wire. A massive, long handle violently yanks the wire far out into a deep, sweeping arc before it loops back to the final destination.
Okay, so the endpoints anchor the wire, the handles pull it, but things get complicated when a single point has lines flowing through it on both sides. Let's say I have a point right in the middle of a continuous wave. How many handles are sticking out of that middle point?
The rules are absolute here. If a point connects 2 perfectly straight lines, like the corner of a square, it has 0 handles. No magnets required.
Makes sense.
If it connects 1 straight line and 1 curved line, it has exactly 1 handle, managing the tension for the curved side. But if it connects 2 curved lines, that single point will have 2 handles protruding from it, one controlling the entrance velocity of the first curve and one controlling the exit velocity of the second curve.
And this is exactly where my designs always fall apart. When I have 2 handles on one point and I try to adjust one side of the curve, the other side gets lumpy and deformed. The book addresses this directly by breaking down the 3 states of handle mirroring.
Understanding mirroring is the absolute key to mastering vector illustration. The first state is no mirroring. The 2 handles act entirely independently. You can move the left handle anywhere, and the right handle stays frozen.
When would I actually want them disconnected like that?
Whenever you need a sharp, acute angle in a curved path, think of drawing the top cleavage of a heart shape. The curve sweeps up, hits a sharp pivot point, and sweeps back down. The handles must point in completely different directions to force the path to change direction sharply.
Got it. Okay, so the second state is mirror angle.
In mirror angle, the software locks the 2 handles into a perfectly straight 180-degree line with each other. If you grab the left handle and pivot it upwards, the right handle acts like a seesaw and pivots exactly downwards.
So they are tied together.
Yes. This absolute alignment guarantees that the curve passes through the anchor point flawlessly, with no sharp corners or bumps.
But they can be different lengths, right?
Correct. The angle is locked, but the velocity is not. You might need a long handle on the left to pull a deep, slow curve, but a very short handle on the right to quickly transition into a tight turn.
Which leaves the final state, mirror angle and length.
The ultimate tool for symmetry. The handles are locked in a straight line, and their magnetic strength is mathematically synced. If you pull the left handle out, the right handle extends equally. This is how you construct perfectly smooth, rhythmic sine waves or precise organic ovals.
Even knowing all that math, beginners still draw what I call lumpy potatoes.
Lumpy potatoes.
The curves just look slightly wrong, slightly amateurish. Why does the mechanical failure happen?
The mechanical failure almost always stems from point placement. Beginners tend to over-engineer their paths. They think, oh, this is a big curve, I better put 5 points along it to guide it.
I am totally guilty of that.
But every point is a mathematical interruption. The first golden rule of vector drawing is minimize your points. Let the Bezier math do the heavy lifting. A massive sweeping curve drawn with 2 endpoints and long handles will always be smoother than the same curve stitched together with 6 endpoints.
The math naturally wants to be smooth. We interrupt it by clicking too much. What's the second rule?
Place your endpoints at the absolute extremities of the curve. Don't place an anchor point randomly halfway up an arc. Put the point at the exact peak of the curve's trajectory.
And the third rule, which blew my mind because it instantly fixed my workflow, restrict your handle angles.
Yes. Holding the Shift key while dragging a handle snaps its angle to strict 45-degree increments, usually locking it to a perfect vertical or horizontal axis.
How does that help?
By keeping your handles strictly horizontal and vertical, you eliminate radical variables. You are boxing the math into a predictable grid, making it exponentially easier to control the symmetry of the shape.
And if you don't want to deal with handles at all, the engine provides the bend tool. You literally just hold the command key, click directly on the curved wire itself, and drag it. The software recalculates the invisible handles behind the scenes for you.
It's like magic. Plus, there's the pencil tool, Shift P, which drops the math entirely and lets you freehand draw.
Capturing the micro imperfections of your hand movement.
Exactly, which is essential if you are drafting on a tablet like an iPad. And because vector networks recognize complex enclosed spaces automatically, you can use the Paint Bucket tool shortcut B to hover over any intersecting web of lines, click, and drop a color fill directly into that specific closed section.
It treats the intersecting vector lines like the lead framing in a stained glass window. That is beautiful. Okay, we have drafted complex paths, we have drawn perfect squircles, but interface design isn't just drawing shapes, it's combining them to build complex components.
Right.
Which brings us to the alchemy of shapes.
We are entering the realm of Boolean groups. Boolean operations allow you to take 2 or more overlapping shapes and merge their mathematical properties to create new geometry. There are 4 distinct operations: union, subtract, intersect, and exclude.
Let's visualize a practical use case. I'm designing an icon for a weather app, a cloud with a lightning bolt cutting through it. I can't just draw that with one continuous line. I draw 3 overlapping circles and a wide rectangle to form the cloud shape. How do I make them one object?
You use a union operation. You select the circles and the rectangle, apply union, and the engine fuses their outer perimeters into a single unified outline. All the internal overlapping lines instantly vanish.
Perfect. Now I have my solid cloud. Next, I draw a lightning bolt shape using the pen tool, and I lay it right on top of the center of the cloud. How do I cut that shape out?
You select both the cloud and the bolt and apply a subtract operation. Subtract uses the top layer as a blade, cutting its exact outline completely through the layers beneath it.
So the bolt just disappears.
The bolt disappears, leaving a perfect bolt-shaped window through the cloud.
Just a cookie cutter. What about intersect and exclude?
Intersect deletes everything except the shared overlap. If you overlap a square and a circle, intersect leaves you with only the exact wedge where the 2 forms occupied the same space.
And exclude?
Exclude is the mathematical inverse. It retains all the geometry but punches a hole entirely through the exact area of overlap.
Now, here is the crucial distinction about how Figma handles this alchemy compared to legacy software. It's non-destructive.
A vital architectural choice. When you apply that union to make the cloud, the software doesn't actually delete the original circles. It creates a special Boolean group folder in your Layers panel. Inside that folder, your original circles and rectangles are still perfectly intact.
Wait, really? So what am I looking at on the canvas?
The engine is just running a live filter to make them look unified.
Meaning, a week later, if the client says the cloud looks too lopsided, I can open the folder, grab one of the original circles, move it a few pixels to the right, and the entire union outline dynamically updates in real time.
Exactly. You are deferring the permanent mathematical commitment.
Which brings me to a major point of contention. The book discusses a command called flatten selection, shortcut command E. It explicitly notes that this is a highly destructive action that permanently bakes the shapes together, destroying the live Boolean groups and fusing the math into one uneditable vector path.
It does.
Wait, if non-destructive workflow is the entire point of modern design tools, why on earth would I willingly use a shortcut that permanently destroys my layers?
It sounds totally counterintuitive, but flattening geometry is actually mandatory for final production. There are 4 specific, highly technical reasons you must eventually press Command-D.
Okay, I'm listening. First reason.
First, accessing new intersection points. Let's return to your cloud icon. You used a union to combine the circles, but what if you need to grab the exact sharp inner point where 2 of those circles melted together and pull it downward to make the cloud look like it's dripping?
Oh, to edit the new shape.
Right, but you physically cannot do that while they're a Boolean group because that specific point doesn't technically exist yet. It's just a visual rendering trick. You have to flatten the group to forge that intersection into a real manipulatable Bezier anchor point.
Okay, creating access to the generated geometry. That makes sense. What's the second reason? I imagine file size plays a role here.
A massive role.
Ugh.
If you hand off a complex icon built from 20 overlapping live shapes to a web developer and they export it as an SVG, the browser has to load all 20 hidden shapes and run the complex Boolean math in real time to render the final image.
That sounds heavy.
It bloats the code. Flattening bakes the entire composition down to a single, hyper-efficient perimeter line, drastically reducing the file weight.
Web performance matters. Reason 3.
Locking directional styling. Imagine a square with a linear gradient fading from dark blue at the top to light blue at the bottom. If you simply rotate that square 90 degrees on the canvas, the gradient rotates with the object. The dark blue is now on the side.
Right.
But if you flatten the square before you rotate it, you bake the shape's coordinates into the global canvas space. You can then rotate the shape, but the gradient will remain permanently locked to a top-to-bottom vertical axis.
That is incredibly niche, but it solves a problem I have literally banged my head against the desk over. And the fourth reason, to destroy the layers.
Taming the bounding box. Remember earlier we established that a star shape has a dynamic bounding box that extends out to accommodate adding more points later.
Yeah, all that extra padding.
If you are trying to perfectly align that star to the baseline of a typography layout, that invisible padding will push the star down, making it look mathematically misaligned to the developer. Flattening the star violently strips away its dynamic properties and snaps the bounding box tightly to the true, visible pixel edges of the shape, allowing for absolute pixel-perfect alignment.
All right, I concede. Flattening is a necessary evil, but the book offers a golden rule of survival here. Always duplicate and hide your original Boolean layers before you hit Command-D. Keep an unbaked version of the cake hidden in the fridge, just in case.
Exactly. Always keep a backup.
Now let's pivot from Booleans to masks, because masks also control visibility, but they use vastly different logic.
Yes. While Boolean groups merge paths mathematically, masks act as viewports. The most common is the outline mask, also known as a clipping mask.
This feels intuitive. It's like taking a giant photograph, laying a thick piece of cardboard over it, and cutting a keyhole in the cardboard. You only see the part of the photograph that shines through the keyhole.
Precisely. In the software, you draw a vector shape, the keyhole set it to act as a mask, and place the image layer above it. The image is clipped to the exact boundary of the vector path. But Figma also supports a vastly more complex rendering feature, alpha masks.
And here we step away from hard vector lines and into pixel data. What exactly is an alpha mask?
To understand an alpha mask, you really have to understand the alpha channel. A digital image is made of pixels, and each pixel contains data for red, green, and blue. But PNG files carry a fourth channel, -alpha, which dictates transparency.
Transparency math.
Yes. It assigns a mathematical value to every single pixel, from 0, which is completely invisible, to 255, which is completely solid white.
So it's literally a map of visibility.
Exactly. When you use a PNG as an alpha mask, the software multiplies the visibility of the image above it by those exact pixel values. So if your mask is a gradient that smoothly transitions from solid white at the top to transparent at the bottom, your photograph will magically fade away into nothingness, perfectly matching the soft, complex transition of the mask.
Hard vector lines can't do soft fades, so alpha masks unlock incredible atmospheric effects. But there is a technical caveat to using pixel-based masks, isn't there? There is. Raster artifacts. Because an alpha mask relies on a grid of fixed pixels rather than infinite math, it has a resolution limit.
Oh, like a photograph stretching.
Exactly. If you design an interface using a tiny PNG alpha mask, and then you scale that entire layout up for a massive desktop monitor, the pixels in the mask stretch. The smooth fade becomes jagged, blurry, and blocky. The illusion entirely breaks.
So we have built the wireframes. We've sculpted the geometry, manipulated the vectors, combined the booleans, and clipped the masks. The structure is mathematically perfect. But a structure has no soul without light, shadow, and color.
Now comes the fun part.
Yes, we're moving into painting the canvas, fills, gradients, and blend modes.
This is where aesthetic impact is forged, and it begins with how we command the engine to interpret color. Most people entering design are familiar with two color models, RGB and hex codes.
Hex codes being those 6-digit alphanumeric strings, like hashtag FFS000 for red. Right, and hex codes are exceptionally useful for a very specific task, copying and pasting a definitive color value into a chat message to hand off to an engineer. It is machine language, but as the text argues powerfully, hex codes are terrible for actual design iteration because they completely ignore human perception.
If I have a hex code for deep maroon and my art director stands over my shoulder and says, make it 15% brighter and just a little more vivid, I can't look at the string hashtag 4AZOZown and intuitively know which letters to swap out. It's cryptography.
Which is why professional designers switch the interface to the HSL or HSB color models. HSL stands for hue, saturation, and lightness. HSB is hue, saturation, and brightness. These models map color to a three-dimensional coordinate system that our brains can actually intuitively navigate.
Let's unpack the math of those coordinates. Hue is the actual pigment, right?
Yes. Hue is represented as a degree on a standard 360-degree color wheel. 0 degrees is pure red, 120 is green, 240 is blue, sweeping all the way back around to red. Saturation is the intensity of that pigment, measured from 0 to 100%.
What does 0 look like?
A saturation of 0 is completely drained of color, a flat, lifeless gray. 100 is the most vibrant neon version of that hue possible.
Okay, but what is the mathematical difference between lightness in HSL and brightness in HSB? They sound like synonyms.
They do, but it's a subtle but massive difference in how the rendering engine calculates white. In HSB, brightness is simply how much virtual light is shining on the color. But if you push brightness to 100%, the color doesn't necessarily become white.
It doesn't.
No, if saturation is also at 100%, you just get a painfully bright, vibrant color. To get pure white in HSB, you have to manually drain the saturation down to 0.
So it takes 2 steps.
Exactly. But in HSL, lightness overrides everything. If you push the lightness slider to 100%, the color turns blindingly pure white, regardless of where the saturation slider is set.
So HSL is a faster path to pastel and white variations. And this human-readable mapping is why I can instantly respond to that art director. Brighter and more vivid. I don't guess the hex code. I just nudge the lightness slider up 10 points and the saturation slider up 10 points. We are manipulating the physics of light directly.
But manipulating light brings a profound ethical and functional responsibility, accessibility. A UI designer isn't painting a canvas just to hang in a gallery. They are building a tool that people must read. The text specifically highlights using plugins to verify WCAG contrast.
The Web Content Accessibility Guidelines.
It is a mathematical ratio. If you place sleek, silver text on a stark white background, it might look incredibly modern and minimalist to you, but a user with a mild vision impairment or someone reading their phone in bright sunlight physically cannot see it.
That's a huge problem.
The contrast plugin calculates the mathematical difference in luminance between the foreground and background layers and validates it against international standards. Designing without checking this math is professional negligence.
It's form-following function. Now let's talk about blending those colors. Gradients. A gradient is a smooth transition from one color to another. The software offers linear, radial, angular, and diamond gradients. But the real value in this chapter is the psychological advice on how to use them.
Modern digital design went through a flat phase, solid, unbroken expanses of single colors. But the text notes that completely flat color feels slightly unnatural to the human brain. Why? Because in the physical world, absolutely nothing is lit perfectly evenly. There's always an ambient light source, and therefore always a subtle gradient of shadow.
So dropping a very subtle, almost invisible monochromatic gradient over a flat background, just a 5% shift toward darkness at the bottom, tricks the brain into perceiving depth.
It injects physical realism, but creating dramatic multicolor gradients is where designers frequently trip up, resulting in what we call the muddy middle.
Yes. Oh my gosh, I'll try to create a vibrant sunset gradient fading from a deep blue to a bright orange. Direct opposites on the color wheel. And instead of looking beautiful, the middle of the transition looks like dirty, dead gray sludge.
What is the mechanical failure happening there?
It's geometry. Imagine the color wheel. Blue is on the left edge, orange is on the right edge. The software has to calculate the shortest mathematical path between those 2 points.
And what's the shortest path?
That path is a perfectly straight line drawn directly across the exact center of the wheel. And the exact center of a color wheel has 0 saturation. It is pure, dead gray. The algorithm literally drags your beautiful colors right through the graveyard to get to the other side.
That perfectly explains the sludge. So how do we force the engine to bypass the graveyard?
The book offers 2 architectural fixes. First, shift the hues so they aren't direct 180-degree opposites. If you pull the angle back to 160 degrees, the line mathematically skirts around the dead center, staying in the saturated zones.
Okay, and the second? Second, simply take manual control, add a third color stop right in the middle of the gradient, and manually force it to be a highly saturated intermediate color, like a vibrant magenta. You are manually bending the path around the gray zone.
That is the definition of commanding the canvas, bypassing the default math. And if we want to get even deeper into visual mathematics, we arrive at blend modes. This dictates not just how a single layer looks, but how it interacts with the pixels beneath it.
Blend modes calculate the base color, the layers underneath, and the blend color, the active layer, to generate the resulting color. They are mathematically categorized. The most fundamental darkening mode is multiply.
Give me a physical analogy for multiply.
Think of physical translucent felt tip markers. If you draw a yellow stripe on a piece of paper and then color over it with a light blue marker, the overlapping area doesn't turn light blue, it turns a darker, deep green.
The inks compound.
The multiply blend mode literally multiplies the RGB luminance values of the overlapping pixels, guaranteeing that the resulting color will always be darker than either of the original colors. It is the absolute optimal way to render deep, realistic shadows because it dynamically tints the shadow with whatever colors are in the background behind it.
Okay, what's the mathematical inverse for lightning?
Screen. The analogy here is light projection. Imagine a pitch black room with 2 slide projectors. One projects a bright red circle onto the wall. The other projects a bright blue circle. Where the 2 beams of light intersect, the wall becomes blazing white.
Because it's light, not ink.
Right. The screen blend mode multiplies the inverse values of the pixels, guaranteeing the result is always lighter. It is how you render glowing neon highlights or lens flares.
There are dozens of these modes. Overlay for boosting contrast. Difference for mathematically isolating misalignment. But the text drives the importance of this math home with the brilliant real-world case study. The People First Jobs website logo.
Oh, this story perfectly encapsulates the danger of using settings you don't mathematically understand. The designer created a gorgeous logo composed of 3 overlapping geometric shapes in different colors. To give it an architectural depth, they set the shapes to the multiply blend mode. Against the website's stark white background, the overlapping areas compounded into beautiful, dark, rich intersections. It looked incredible.
But then the internet shifted. Dark mode became an industry standard.
Exactly. The engineering team flipped the website's background from white to dark charcoal gray. And suddenly, the logo completely collapsed. Because multiply always darkens the result, taking 3 already dark colors and multiplying them against a charcoal background resulted in the overlaps turning into a pitch black, illegible stain. The logo was ruined.
So an amateur designer would panic, tear the file apart, and rebuild a completely separate logo just for dark mode. But a designer who understands the matrix of the tools realizes they just have an inversion problem.
They did exactly what you would expect. They looked at the math. If multiply is the algorithm for compounding darkness on light backgrounds, what is the exact inverse algorithm for compounding light on dark backgrounds?
String.
They selected the layers, changed the dropdown from multiply to screen, and the problem vanished. The overlapping sections stopped compounding ink and started acting like intersecting beams of light. They became bright, luminous, and vivid against the charcoal background while preserving the exact original structural geometry of the logo.
It's an elegant one-click solution, but you can only arrive there if you know why the click works.
Right.
And one final clarification on transparency while we are here, layer opacity versus color opacity. If I want a blue square to be 50% see-through, which one do I use? Does it matter?
It vastly matters for the scalability of your design system. If you adjust the layer opacity, you are turning down the volume on the entire object, the fill, the stroke outline, the drop shadows, everything attached to that bounding box fades out universally. But if you adjust the color opacity, you are only making the blue pigment itself transparent.
Why is that better?
Because Figma allows you to save colors as global styles that can be applied to thousands of objects across your entire file. You cannot save a layer opacity to a style. If you want a specific frosted glass, semi-transparent blue that you need to use consistently on 50 different screens, you must dictate that transparency at the color opacity level, so it is permanently baked into the global style definition.
System-level thinking. I love it. Okay, we've covered the shapes, the paths, the colors, but a modern interface communicates primarily through words, which means we have to address text, and the text engine is shockingly deep.
Typography is the structural spine of UI design. You initialize it with the T shortcut, but immediately you are faced with a behavioral choice when creating a text block: auto width, auto height, or fixed size.
This trips up beginners constantly. If I just click the canvas once and start typing, it defaults to auto width. The text box just grows horizontally forever on a single line until I hit enter.
Which is perfect for a single button label or a short headline. But if you click and drag a box, you create a fixed size container. The text will automatically wrap to the next line when it hits the edge of your box. This is vital for designing responsive mobile layouts where the screen width is heavily constrained.
Once the box is built, we have to pick the typeface. And the text notes, we aren't just picking a font, we are managing a complex triad of metrics: font size, line height, and letter spacing.
Font size is obvious, but line height, the vertical space between lines of text, is where readability is won or lost. In UI design, line height shouldn't be arbitrary. It needs to lock into the mathematical grid of the interface.
The grid.
If you are using an 8-point structural grid, your line height shouldn't be 21 pixels. It should be mathematically forced to 24 pixels, so it consistently snaps to the invisible baseline grid across the entire page.
And letter spacing, or tracking, requires optical adjustment. A massive, bold, 60-point headline usually needs its letter spacing tightened slightly into negative values so the characters feel cohesive. Conversely, tiny 10-point microcopy needs its letter spacing expanded positively so the letters don't bleed together on a low-resolution screen.
And here is a critical mechanical warning regarding scaling text. Remember our earlier discussion about the Move tool versus the Scale tool?
Yes, the container versus the content.
If you grab the corner of a text box with the Move tool, you are only making the container larger. The text inside stays exactly the same size, it just reformats to fill the wider box. If you want the physical typography to grow bigger, you must switch to the Scale tool, Kay.
Because it multiplies everything.
Exactly. The engine will recalculate the font size, the line height, and the letter spacing simultaneously to perfectly magnify the type block.
It's the photocopier effect again. What about the advanced features? The book touches on OpenType and vector conversion.
OpenType features are hidden algorithms embedded directly into modern font files by the typographer who designed them. In the advanced type settings, you can toggle these on. They dictate whether numbers all sit flat on the baseline or bounce up and down in an old-style arrangement. They control complex ligatures, like forcing the letters F and I to melt together into a single, elegant glyph when they are typed next to each other.
And icon fonts leverage this too, right?
Yes. Fonts like material symbols allow you to simply type the word home, and the OpenType ligatures instantly intercept that string of letters and dynamically swap it out for a vector graphic of a house.
But what if I need to alter that house icon? What if I want to use the pen tool to delete the chimney? I can't do that while it's recognized as text.
Which is when you execute a vector conversion. By right-clicking and selecting Outline Stroke or Convert to Paths, the engine violently strips away all the typographical data. It forgets the font name, the line height, the spell check, and converts the visual letter forms into raw, editable Bezier curve vector networks.
Highly destructive action, much like flattening Booleans. You can't ever type in that box again.
Exactly. You only convert text to paths when you need to manipulate the literal geometry of the letters, like connecting them to draw a custom logo.
We are nearing the end of the pipeline. We have built the design perfectly, but we don't design in a vacuum. We have to hand this over to the engineering team, which means exporting, sectioning the canvas.
The primary vehicle for this handoff, particularly for icons and logos, is the SVG export.
We talked about importing SVGs earlier, teleporting the math. Exporting is just writing that text file for the browser to read. But the book highlights a specific tool here, the Slice tool, shortcut S. If I can just select an icon, click the export button in the corner, and save it, why does the Slice tool even exist?
Because the mathematical boundary of your icon might not match the structural requirement of the web layout. Let's say you drew a simple thin arrow icon that is 14 pixels wide and 8 pixels tall. If you just select the arrow and export it, the resulting SVG file is exactly 14 by 8 pixels.
That sounds correct.
But standard touch targets for a mobile phone screen dictate that any tappable icon should sit inside a bounding box of at least 24 by 24 pixels to ensure the user's finger actually hits it. If you hand the developer a 14 by 8 file, they have to write extra code to pad it out and center it.
So the slice tool allows me to define a separate export boundary.
Exactly. You activate the slice tool and draw a rigid 24 by 24 pixel square precisely centered over your little arrow. The slice doesn't visually alter your design at all. It acts as an invisible designated export zone. When you export that slice, the engine generates an SVG that is perfectly 24 by 24 pixels, with your arrow perfectly aligned inside it, surrounded by pure empty space. You are controlling the spatial footprint of the asset independent of the geometry itself.
You're doing the developer's formatting work for them before the file even leaves your computer.
It is the final mark of professional mastery.
Okay, we have excavated the foundation. We have covered a monumental amount of ground today. Let's trace the journey. We started with the sheer physics of the canvas, understanding that the movie tool shapes containers, while the scale tool multiplies mathematics. We abandoned the destructive pathfinding of the past by embracing fluid geometry, manipulating the sweep of an ellipse.
We decoded the apple squircle, learning why continuous clothoid curves soothe the human eye, but break the CSS rendering engine. We explored the elasticity of raster images, acting as textures painted onto vectors.
We mapped the vector revolution, leaving the linear train tracks of legacy software for the complex graph theory of vector networks, and we defined the tension of the magnetic Bezier handles.
We executed the alchemy of shapes, using Booleans to non-destructively sculpt geometry, and understanding the precise, highly technical reasons why we must eventually destroy those layers by flattening them. We navigated the alpha channel to create atmospheric masks.
And finally, we painted the canvas. We mapped human perception through HSL coordinates, bypassed the dead gray zones of gradients, and illuminated the underlying math of blend modes, proving that screen and multiply aren't just aesthetic filters, they are light physics. And we locked it all into a rigid baseline grid with professional typography and perfectly sliced SVGs.
By understanding these underlying mechanics, you graduate from a user interface decorator into a true systems architect.
And as we wrap up this custom deep dive, I have a specific request. If you found this breakdown valuable, if you want us to keep building these highly technical, custom-tailored deep dives to accelerate your career, explicitly request it by hitting that follow button right now for more technical design breakdowns and career-building content. We are here to help you navigate this complex cockpit.
Knowledge fundamentally alters perception.
It does. So I'll leave you with this final lingering thought. Tomorrow morning, when you pick up your phone and open your favorite app, stop looking at the content. Look at the architecture. Stare closely at the corners of the cards and try to spot the smooth acceleration of a squircle. Look at the drop shadows and try to deduce if the designer used a simple black layer opacity or if they mathematically injected the background color using a rich multiply blend mode. Once you understand the basic elements, the digital world around you stops looking like a flat pane of glass. It becomes a matrix of geometry and light, and you can finally read the code.